Hey everybody, how's it going? Today we are going to talk about solving exponential equations. Our EQ is how and when do you use logarithms to solve exponential equations? Well, we can answer that partially right now by just remembering the fact that exponentials and logarithms are inverse operations of each other. And if you can use that clue to help you remember that we use inverse operations to solve equations, exponentials and logs are inverse operations of each other, you're going to be well on your way. Before we get to that part, we're going to actually try something a little bit different. And that is stuff that we've actually already used in a really intuitive way, provided we have a few things already known. Now, you can solve for a variable in an exponent very easily if you write both sides with the same base. So as long as we can get to the same base, that's what we want. And so usually that means trying to reduce and utilize properties of exponents. So for my first example, solve 27 to the x equals 1/3. Well, let's try to rewrite this. And I can change this base to be a base of 3, where that's 3 to the third to the x power. And then 1/3, I realize that this is really like 3 to the first power, but it's in the denominator. And anything that's in the denominator is going to get an exponent, so a negative exponent. So that's like 3 to the -1. And so now I can recognize that, hey, this is power to a power property, which means I just multiply those exponents, and we have 3 to the 3x equals 3 to the -1. And what we hopefully want to recognize here is that as soon as we have the same base, the only thing I really have to care about is the exponents. Now you've already done this to some extent, so that's good. So now we can look at this and just say, I don't care about those. I'm turning this into a super simple algebra 1 problem. All I got to do now is look at the exponents, use that equation, divide by 3, and I will get my answer. X is equal to -1/3. So what that tells me is 27 to the -1/3 power will indeed give me 1/3. My answer checks out. I could punch that into a calculator if I wanted to. The next one's a little bit more complicated, but it still utilizes the same skills. So this is where you really have to step up your game a little bit. The first one has a base of 2. Well, that's as small as a base as I can get. But I look at this one, I've got a fraction again, and I have this 16. Well, 16 is a power of 2, so we can rewrite that. 8 is also a power of 2. So let's go ahead and rewrite the equation. First one I can't do anything with, but the next one, I can write this as 1/2 to the 4x, because 2 to the 4th power is equal to 16. And then here, I can write 2 to the 3rd power. That's the same thing as 8. And that's now to the -2 minus x power. Now what we want to do is maybe try to rearrange these a little bit, make things a little bit easier for us. One thing I do remember, the first one, again, I can't really do anything else with, but this next one, again, I can rewrite this as being in the numerator, provided I use a negative exponent. So that becomes 2 to the -4x. And the next one, I can go ahead and distribute this exponent 3 to each of these terms, because that's the power to a power rule. And that becomes 2 to the -6 minus 3x. So it's like algebra 1, but we're just doing all of that algebra 1 inside the exponents. That's it. Okay. Next one, this is another one of our power rules, or our exponent rules. When I'm multiplying two numbers with the same base, I can just add their exponents together, writing it with the same base. So that'll be 2 to the 2 minus x plus a -4x. The right side doesn't change, there's nothing really left to simplify, but now this is starting to look like what we had over here in this previous example, where we have two sides with the same base. The only thing I then have to do is focus on the equation that's made by their exponents. So I'm going to go ahead and simplify why I do this. This is going to give me 2 minus 5x on the left-hand side, minus 6 minus 3x. Rearranging this, I'm going to move all of my exponent, or all my variables to the right-hand side. So that's going to give me a positive 2x on the right-hand side after I add then 5x. Adding 6 to the left-hand side, that's going to give me 8. And then this is pretty simple algebra at this point, just dividing by 2. And we have 4 equals x. And look at that. Very elegant, very clean, and actually really, really clever. Okay, so think of these like a puzzle, and it becomes a challenge for you that's actually somewhat engaging, and dare I say, even a little fun. Come on, you know you love it.
All right, let's go ahead and take a look at some other different ideas here. Now, sometimes it's not possible to have the same base on both sides. And when it's not possible to write both sides with the same exact base, we use logarithms. Again, this is where we utilize that inverse idea. Now, for this, we can do two things. We can either use the definition of logarithms, which is this: a to the x equals b is equivalent to log base a of bx. Another way you can think about it is you can solve by rewriting as a logarithm, or we can take the log of both sides. That's our other option. So this is more the algebra way of doing things, and it actually gets pretty interesting of how it can actually work, and we'll still utilize some other different properties of logarithms here. Okay, so let's go ahead and try to do this first one. Example number 3, solve 3 to the x equals 5. And this seems really straightforward, except I don't know off the top of my head what exponent do I raise 3 to get 5. That's really complicated. I need a calculator for this, but before I can even get there, before I want to do any guess and check, I want to have a calculator just do it for me. Okay, so if we were to rewrite this as a logarithm using this definition of logarithms, log base 3 of 5 equals x. And the idea here, if you're struggling remembering what it is, your exponent is generally going to be the answer. So if your variable is in the exponent, this is a perfect strategy to use because it already isolates x. It's rewriting using some basic understandings of logarithms and exponentials to be able to have an already isolated equation. And now it's super simple. We can plug in and use a calculator for this. Now you have to have the right kind of calculator that can actually utilize different bases. Now the calculators we will be using in class, or the one that I'm providing for you through Canvas, you're going to have access to a calculator that can evaluate at these different bases. There's something else that you may use, and that's called the change of base formula. And if you move on into a more advanced math course after this that focuses a lot more on algebra, you will end up writing either this as your answer, or you will end up writing in something you can evaluate using the change of base formula. But we are not going to cover that, at least not yet in this course. Okay? So we don't need to worry about that. We can plug this into a calculator, and the answer we get, if we plug this into a calculator, is going to be 1.46497. It's going to be an irrational number, which means it goes on and on and on forever, and it never stops. But we don't like that in IB. What we end up doing is we round to 3 significant figures. We'll get more into 3 significant figures, but basically you can look at it for right now. We'll just go ahead and round to 2 decimal places, and that's 1.46 equals x. So 3 to the 1.46 power will give me approximately 5. Okay? Now, example number 4. This one is, I'm not going to lie, it's a doozy, but it's awesome. We're going to save it for last. Let's go ahead and turn the page and look at example number 5. So this method really only utilizes that definition of logs. We're going to utilize that definition of logs here, but we will also show you example number 5, solving by taking the log on both sides. So let's get to that one. Okay? The first thing that we want to do whenever we are faced with this kind of situation here is if we've got a lot of different operations happening outside of the exponential part, right? I've got this multiplying by 4. The first thing I want to do is isolate the base. Whatever it is that I have an exponent with, I want to isolate the base and the exponent. Okay, now we don't want to reduce anything. We always want to reduce at the very end. Do like the basic algebra stuff at the very end. Okay, so let's go ahead and do step 1. We're going to divide both sides by 4, and that's going to give me 9 to the 2x over equals 10 over 4. Again, don't reduce yet. That's for suckers. That's like, doing extra work when we don't need to yet. It might take care of itself on its own. So just wait for a little bit. Now, step 2. Rewrite as a logarithm. This is using that definition of logs. Okay, so we have step 2 is writing this as log base 9 of 10 over 4 is equal to the exponent 2x. Okay, now you can start to see like, oh, we've almost got our variable isolated. So let's go ahead and do whatever basic algebra we need to isolate our variable. We do that by dividing both sides by 2. You might think, can we divide an entire logarithm by 2? Absolutely. Log base 9 of 10 over 4. It's got 2 operations in it, the logarithm and the division, but really it's just a number that's just waiting to be evaluated. So we can still divide by 2, that's no problem. I can even punch this directly into a calculator. Okay, so now we see that the 2, that divides out nicely, but guess what? You are le dunzo. This problem is solved in just a few steps. Okay, so step 4, our answer, if you were taking the ACT that covers a lot of logarithms, if you were working in a calculus-based class, this would probably be how you'd write your answer. Okay, however, we can go ahead and reduce if we need to, or we can plug it in to a calculator. Okay, but our official answer, we could write it, this would be the exact answer because we are not having to do any kind of rounding or anything like that, just reducing the fraction. This would be a perfectly acceptable way to have your answer written. Okay, now let's go ahead and try the other method. The other method is where we are going to take the log of both sides. Well, step 1 is the same. Okay, step 1, we are still going to isolate our base. So step 1 is going to really be the same thing. We are dividing both sides by 4. And we have 9 to the 2x equals 10 over 4. Now, step 2. Take the log of both sides. But here's the important part. You have to use the base of your exponential. This is the critical part here. Nothing works if you don't use the same base. Okay? So, what we mean is we'll say, I'm going to say log base 9 of 9 to the 2x. Now I have to do the same thing to the other side. Log base 9 of 10 over 4. Okay? It seems weird, but it's still doing the same kind of thing in any other algebra. As long as you do the same thing to both sides of an equation, you're fine. You're not breaking any rules. You're writing the same relationship. It's equivalent on both sides. Now, why does this matter? Because if we are taking the log of the same base, we'll see something magical happen. The log of the same base property says log base 9 of 9 to the 2x. You think about those as like canceling each other out, and the only thing that you're left with is 2 to the x. The property that we used here is log base a of a to the x equals x. And you can verify yourself with our property of logarithms notes from section 2.5 that you will see where that comes from. Okay, so now we have 2 to the x equals log base 9 of 10 over 4. But doesn't that look familiar? It's the exact same thing we had over here. So it's maybe doing one more step, but it's still the same idea. Okay? Divide both sides by 2. And we get our same results. You can write the exact answer if you want, or you can evaluate it in a calculator. Since I don't have access to a calculator right now, this is how I'm going to leave it, and here is my answer. All right, let's go ahead and now come back to example number 4, because I said this one is a doozy. This is a really great problem, and if you start to appreciate the cleverness, the elegant way that we can solve this, and how it turns this something that's so gross actually has kind of a somewhat neat solution. If you appreciate this, then again, this is where you can start to see, oh man, I kind of geek out on this. This is a really good problem for you to assess whether you want to look at Math AA, the Approaches and Analysis course, or Math AI. It's not about difficulty, because each one is difficult in their own different and unique ways. But this one is really just more of a pure mathematics and appreciation of the beauty of mathematics kind of thing. And that's where AA will really kind of take you. So what we want to look at here is that I've got two numbers in this equation that have the exponent with a variable. The problem is they have different bases. And we immediately think, well, I'm stuck. I can't do anything here. But you can if you are just persistent and you start to find the puzzle pieces to know where to go next. You have to kind of like play detective and just look for the clues, okay? So here's what we can do. We can take the log of both sides. And you think, wait, you just told me earlier that the logs have to be the same base if I'm going to do that. Well, if your bases are different, you can use any log you want. It's just going to look really gross at first, but we'll start to see how we can put it together, okay? So let's go ahead and take a look at this one. I'm going to take the log of both sides using parentheses. And you notice that I didn't write a base, so I'm using the common log base 10. For each one, just because it doesn't matter. I could use ln, I could use log base 8, it doesn't matter, really it doesn't. Now, what I want to do next, it seems again like, well, what did that do? I'm stuck still. A lot of students will want to try and divide by logs. You can't divide by just log and have log cancel out. It's not how it works. What we want to do is be persistent. Keep using properties of logs. Don't stop. Just keep going. Your goal is to try and get your exponent with the variable out of the exponent. And we'll start to see ways in which we can do that. Okay? So let's go ahead and first separate out the first one here. This is the product property. I'm going to replace this with a dot for the multiplication, not to confuse it with the variable x. Okay, the product property with logarithms says if I'm taking the product of a log, or I'm taking the log of a product, then I can separate that into two different logs, separated by an addition sign. Okay? And now I'm going to start to recognize something else I can do with the right-hand side. I'm going to do that in just a second, but the left-hand side, I still want to try and break this apart a little bit more. So now, let's try another strategy. This first one, log base 1.27, this makes me happy because this is really just a number. That's something I can punch into my calculator, okay? That's actually a really good thing. Even though it looks gross, it's a good thing. So I'm going to just leave that put. Now with this one, what I want to recognize is that this is, I'm subtracting two values, right? Well, it's kind of like doing division of logarithms or even the product of two different logarithms, okay? Or two different values. I'm going to rewrite this in a somewhat clever way. I'm saying this is going to be the same thing as log of 7 to the 2x times 7 to the negative 1. Because by the same idea here, the product of two numbers with the same base, I can just add the exponents to give me this guy right here. Okay? So let's see how that's going to help us out in just a moment. But I said I can do something with the right-hand side that's going to help me out. Remember that an exponent can always come into the front. So this is going to be now x log base 10 of 5. That's actually really powerful because now the x is out of the exponent, and that's what we want to do. We want to try and get the x's out of the exponents. So let's think about what we can do here. Well, next step, I have log base 1.2 or log of 1.27. I can again separate these two and I can move my variables out of the exponent. I can say this is going to be the product of two logs, which means I can add them. Log base 7 of 2 to the x plus log of 7 to the negative 1 equals x log 5. Again, I'm just separating these out by using that product of logs property. Okay. Now, let's go ahead and try and get anything out of the exponent. Let's get the 2 to the x out of the exponent, and let's get the negative 1 out of the exponent. So this now becomes log of 1.27 plus 2x log of 7. The negative 1 comes down, turning into negative 1 log, or just log, negative log of 7, equals x log 5. Okay? Don't get intimidated by all these different logarithms and all the different notation. You just got to keep things in order. I don't think about log as something really gross. I think about it like a or b or x. It's just some like variable. It's just a piece. The piece just looks bigger. So don't get intimidated by that. Just recognize that that's a piece to move around. Okay? Now, what we want to do is basic algebra. Get the terms with your variables to one side. Okay? So I'm going to move the x log 5 to the left-hand side, and I'm going to do that by subtracting. Minus x log 5 minus x log 5. Okay? But now, any term that doesn't have a variable, I'm going to move it to the other side. So now I'm going to subtract this log of 1.27, and I'm going to add this log of 7. Okay? It's okay to move around entire pieces. That's just one big piece. That's all it is. It's still a number, just a weird looking number. So now what we should recognize is that on the left-hand side, the only things we have left are the 2x log 7, and then on the other side, we moved over that negative x log 5. Then we end up with, on the right-hand side, what did we move? We have log 7 minus log 1.27. Remember what I said about trying to simplify things. Simplifying in the middle is for suckers. Don't do it. Leave it to the end. It seems like it's more writing, but it's easier to work with, okay? Now, here's the next clever part that I want to recognize. I have a common factor. Let's factor it out. Okay, so if I factor out x, I'm left with 2 log 7 minus log 5. And you can see very easily if you were to factor that, or if you redistribute that x, you would get the same thing as what you had on the left-hand side, but I don't need to do that right now. Okay, and then the right-hand side, nothing has changed. These two terms, they don't subtract. We don't want to write anything else crazy like that. Okay, we're just going to leave it as it is right now. Okay, but now here's what we can do. I am multiplying this x through to all of these 2 log 7 minus log 5. Well, what can we do? What's the inverse operation of this multiplication that I'm doing here? It's division. Again, I don't have any variables there. 2 log 7 minus log 5, that's just a number. Let's go ahead and subtract, or let's go ahead and divide that number. 2 log 7 minus log 5. I'm going to divide everything. 2 log 7 minus log 5. And what you want to recognize here is that, oh, look what I just did. That cancels out. That cancels out. Let's try a different color here because that didn't show up very clearly. The 2 log 7 minus log 5 cancels out on the left-hand side. Okay? Now, what you want to see is what do we have left on the left-hand side? Just x. we've solved for it. Now what's on the right hand side looks really gross, but this is something you could punch into a calculator and you would be completely simplified at that point. It looks super gross, but we have now solved for x. So if this is something that looks appealing to you and really interesting, then by all means, like, hey, we can work with more kinds of problems like this. This should get you excited for the next step, right? If not, still take these ideas and that persistence of working with and utilizing every single property. Be a detective, look for the clues, look for the pieces, look for the puzzle pieces to put it all together and to go from one step to the next. Keeping in mind what your goal is ultimately, and that'll help you get there. All right, so the next couple of examples, in the interest of time, I'm not going to work on those right now. I want you guys to take a look at the completed notes for those very last examples that are applied questions that'll really kind of maybe see the marriage between logarithms and the real world. Otherwise, you guys are ready to go and look at your assignment. Have a wonderful day. I will see you next time.